In this video, we're going to talk about walks, trails, and paths. We'll define these, look at an example of each, and finally, prove Theorem 2.1. So let's take a look. Recall that a UV walk in a graph is a sequence of vertices that begin at U, end at V, and where any two consecutive vertices are adjacent. Now a trail is a special kind of walk. It's a walk in which no edge is repeated. And a path is also a special kind of walk. In this case, it's one in which no vertex is repeated. We also want to keep in mind that the length of a walk is the number of edges that are encountered in the walk. So let's take a look at some examples. So here I have this walk W1, and this is the notation we use for walks, trails, and paths. Right? We use ordered tuples of vertices. So here we have, W1, X, W, Y, W, V, U, W. So notice that this satisfies the conditions. So this would be an example of a XW walk. And let's check. So XW, so that means there should be, these are consecutive vertices, so there should be an edge between X and W. Yes, there is. So XW, WY, so from W to Y, those are adjacent. Y to W, so back along this edge, back to W. W to V, V to U, and finally U to W. And that's W1. So notice, every two consecutive vertices were adjacent. And so you can think of this like we're proceeding along the graph by following edges in a consecutive way. That's what a walk is. So this is an example of an open walk. So not only is this an XW walk, but this is an open walk, because the starting and end vertex are different, right? XW. A closed walk would be one in which the starting and end vertex are the same. So let's take a look at a special kind of walk. This is a trail. So here I have the example T, U, V, Y, W, V. So I'll use red for this one. So U to V, V to Y. Again, any two vertices are adjacent. Y to W, and W to V. So notice I didn't repeat any edges. I did repeat a vertex, right? V occurred twice. That's okay with a trail. We're allowed to repeat vertices with a trail, but we just can't repeat edges. So no repeated edges, great. That's really a trail. And finally, we'll take a look at P prime here, which I'm claiming is a path. So a path, we can't repeat vertices, and necessarily then we won't be able to repeat edges either. So P prime, U, V, W, Y. I'll use green for this one. So U to V to W to Y would be my path. So that's a UY path. UY path. T was a UV trail. And let's take a look at the lengths of these. So this was an XW walk. So the length is the number of edges that are encountered, not the number of vertices, number of edges that are encountered. So that should be one less than the number of vertices, and that is with multiplicity, the number of edges with multiplicity. So this one, XW, that's 1, YW 2, WY, that's 2, YW 3, WV 4, VU, that's 5, UW, that's 6. So this is a walk of length 6. Length 6. My trail here was a UV trail of length 1, 2, 3, 4. And finally, UY, this was a path of length 1, 2, 3. So that's walks, trails, and paths. Every path is a trail, but not every trail is a path. Every trail is a walk, but not every walk is a trail. finally, let's take a look at theorem 2.1. So what this theorem is saying, so given any two vertices of a graph, any UV walk that I find can be made into a UV path. That is, for every walk in G, there exists some UV path such that every edge of that path belongs to W. So the idea of the proof here is to, and this is a common technique we'll see in this section and throughout this course, that's to look at a minimum walk or some sort of minimum example in general. So proof, so I want to show for every UV walk in G, we have a UV path. So let W be a UV walk in the graph G. And I want to turn this into a path such that every edge of that path belongs to W. So let's say, no, I don't think I want to name this. So we'll just give ourselves a UV walk. And then what I want to do is I want to take a shortest UV walk. So this is one example of a UV walk. So I want to say among all UV walks, and I'm going to call this P, be one of the smallest of the minimum length. Maybe I should say one with the minimum length. Among all UV walks, I guess I want to be a little bit more specific here. Among all UV walks whose edges belong to W, walks whose edges belong to W, let P be one with minimum length. So there's a lot, in general, there could be a lot of walks from U to V whose edges belong to W, and we're going to pick the one of smallest length. So let's actually identify what our walk here is. Let's give ourselves some variables. So let's say P is the walk. We'll start at U, right? UV walk. So U, and I'll label this the first vertex U0. It's a common thing to do. U1, we proceed to U2, and so on up through UK, which will be V, my last one. So this would be a UV walk of length K that we're claiming the shortest is the shortest one, whose edges belong to W. Is a UV walk of minimum length. So in particular, length K is the smallest length. So I claim that this is actually a path. I claim that all of these vertices are actually distinct. So suppose P is not a path. Well, what does that mean? If it's not a path, I mean, we know it's a walk. So if it's not a path, that means I must repeat a vertex, that two of these vertices are not distinct. P is not a path. Then two vertices are the same, or is repeated. Maybe we'll say then, then two vertices are the same. Say Ui is equal to Uj for some 0 less than or equal to I less than or equal to, or strictly less than J, less than or equal to K. So two of these vertices must be the same. And the idea here is then to delete all of the vertices between these. So that is, let P prime be the walk obtained by deleting all of the vertices between ui and uj, by deleting ui plus 1, ui plus 2, however long it takes to get to uj. We'll delete all of those. So p prime is the walk u0 or u1, up through ui. I've now deleted all the vertices between ui and uj, including uj, because that was repeated. So ui, which is the same thing as uj, up through j plus 1 now, uj plus 2, and finish off the rest of the path to uk, which is v. So all we did was delete edges from P. So every edge of P prime belongs to P, and hence belongs to W. So P prime has the property that every edge belongs to W. And what's more is we just deleted some vertices since since there were at least one vertex between ui and uj. We deleted at least one vertex, and hence we got a shorter walk. Belongs to w and has length less than k. Well, so that's a contradiction. This contradicts P having minimum length. And that's the end of the proof. So that is, P must have been a path. P must have actually been a path. So what this theorem is saying is, yeah, anytime we have a UV walk, we can transform that into a UV path simply by picking the smallest of all UV walks. And we'll be guaranteed that every edge of that walk belongs to W, or every edge of the path belongs to W. So that's the idea. All right, join me next time. We'll talk about adjacency matrices.